Hello, welcome back to my presentation on pH, acids and buffers. We'll go straight into the buffers part now. So, if we take a weak acid, because the acid is mostly unionized, in other words, because the equilibrium in front of you is shifted so far to the left, if we chuck in a few more H plus ions, most of them will associate with the conjugate base and form the complete acid molecule. In other words, according to Le Chatelier's principle, the equilibrium will shift further to the left. Now, this means that the hydrogen ion concentration will not change, but there's a limit to how much we can do that because there isn't very much conjugate base, because the acid isn't very ionized. However, we can get around that by adding a salt of the acid. That will provide us with plenty of conjugate base. And what happens therefore is, in this example of propanoic acid and sodium propanoate, the propanoate acts as an acceptor of H plus and becomes propanoic acid. The propanoic acid becomes a donator of H plus. So if H pluses are added to the solution, they associate with the propanoate, and if H pluses are removed from the solution, the acid will dissociate to replace them. So we have a buffer that maintains a steady pH concentration of hydrogen ions. So let's have a look at a calculation based on one of these then. We've got ethanoic acid and sodium ethanoate here. The acidity constant is 1.7 times 10 to the minus 5. And the equation for that is shown. Hydrogen ion concentration multiplied by ethanoate concentration divided by ethanoic acid concentration. Now we can make some assumptions again, as we did before. The first assumption is that all the conjugate base comes from the salt, because the salt fully dissociates and the acid only very partially dissociates. Second assumption is that hardly any ionization of the acid occurs, so the acid concentration is the same as the concentration at the start when you made up the solution. Based on these assumptions, the equation is relatively simple. The acidity constant equals the hydrogen ion concentration multiplied by the ratio of the salt divided by the acid concentrations. If you rearrange that equation, you get this. The hydrogen ion concentration is equivalent to the acidity constant multiplied by the ratio of acid concentration divided by salt concentration. So let's have a look at a calculation for this. We're going to use an example of nitrous acid and its salt, sodium nitrite, and we're going to look at ratios of 1 to 3 or 3 to 1. You wouldn't normally want to have a big ratio like 1 to 10 of acid to salt or salt to acid, because you're limiting the molecule's ability to accept and donate protons in the way I described earlier. So a 1 to 3 ratio is more realistic. So if we have a look at 0.01 molar nitrous acid and 0.03 molar nitrate salt, this is our original formula. The acidity constant equals H plus multiplied by nitrate salt concentration over acid concentration. If we solve that for H plus is acidity constant multiplied by acid over salt, 4.7 times 10 to the minus 4 multiplied by 0.01 divided by 0.03. Note at this point that could be 1 molar and 3 molar. It could be 1 times 10 to the minus 5 molar and 3 times 10 to the minus 5 molar. We're just looking at a ratio. For this calculation, the pH is minus log 10 of 0.000157, which gives us a pH for this buffer of 3.81. That's for a ratio of acid to salt of 1 to 3. If we switch that now and we have a ratio of 3 to 1, do the same concentration calculation, but we've just reversed 0.03 and 0.01. On this occasion, because there's more acid and less salt, we get a higher pH. The pH value is 2.85. It should be clear, but I want to explain it in a more detailed way to you, that if we have the same concentration of acid and salt of acid, then the pH of the solution is equal to the acidity constant. I'll show that in an example. We're looking at hydrocyanic acid and the salt of that acid, sodium cyanate. If we have 0.1 mole or 0.1 molar of each, and the acidity constant is 4.9 times 10 to the minus 10, then the pH is going to be the negative log of 4.9 times 10 to the minus 10, and the pH will be 9.3. Don't worry about the fact that you're getting an alkali pH when you're using an acid in a buffer. It's because you've got the salt of the acid, and it's because you've got a very low dissociation constant for this particular acid. So I'll summarize this presentation with a list of equations that would be useful for you to be able to remember. For each of these, remember that if you're dealing with a diprotic or a triprotic acid, you have to adjust the concentration of H+ ions accordingly. However, for a strong acid, the pH is just the negative log 10 of the concentration of that acid. For a weak acid, it's negative log 10 of the square root of the dissociation constant times the concentration of the acid. For an alkali, work out the pOH as if it was an acid, and then subtract that from 14. For a buffer, the pH is equal to the acidity constant of the acid if the concentration of acid and concentration of salt are equal. If they're not, the pH is equal to the acidity constant multiplied by the acid concentration divided by the salt concentration. Have a little read through this again, have a little practice on your own little examples, and best of luck with answering those in an exam.